Yeah, so good evening, everyone. So today we will be dealing with the week 6 session of NMR of the NPTEL course, NMR Spectroscopy for Chemists and Biologists. So I hope all of you have gone through the week 7 lectures. So what I will do today is I will explain a few of the concepts related to the topics that are being taught, and these concepts will help you solve the weekly assignments that are asked. So I will wait for a few minutes. So we'll wait for 5 minutes and then I'll start the session. So if any one of you have any doubts in the previous related to concepts that were there in the previous session, or some previous concepts that were discussed, you can ask me. I will wait for another 2 minutes and I'll start today's session. So in this session, what we will mainly look into is the quantum mechanical principles of NMR spectroscopy. So I will deal with concepts related to density matrix operations. Then we will further move into equilibrium density operators and further and other related concepts today. A few of the questions that I will discuss today were asked in the week 6 assignment, and also a few concepts that will help you in solving the week 7 assignment as well. Uh, okay, so I will start sharing today's slides, and I'll start today's session. Uh, yeah. So hello everyone. I'm Akash Jyoti Pathak. I'm a PhD scholar in the Department of Biosciences and Bioengineering in IIT Bombay. And I am a PMRF TA for this NPTEL course, NMR Spectroscopy for Chemists and Biologists. So today, today is we will be dealing with the week 7 problem solving session of this course. And so let's start today's session. Yeah, so first we will look into what are operators in quantum mechanics. Uh, so so what are operators? So operators are mathematical entities. Operators are mathematical entities that correspond to physical observables like position, momentum, energy, and spin. So anything that can be measured. That like position, momentum, energy, all these measure quantities, physical quantities that can be measured are called operators. So uh, we have looked into the nuclei. So a nuclei has different can has a particular spin, and it also has an energy. It has an energy, momentum, and a position. So if we want to measure these quantities, so these are called the operators. Now, these operators are crucial for describing the behavior of nuclear spins under the influence of magnetic fields and radio frequency pulses. In NMR spectroscopy, the basic concept is that nuclei is placed in an external magnetic field, and RF pulse is applied. In presence of these magnetic field and radio frequency pulses, if we want to measure quantities like what is the energy level in which the nuclei is present, what is the because of the nuclear spin, what is the angular momentum that is associated with it, and what is the position. Such things can be described if we understand the concept of operator. So in mathematical terms, if A A on top of it you have a hat, so A hat. So this is the symbol which is used to express and denote an operator. So any alphabet which has a hat on top of it is called an operator. And psi is a quantum state. So this is a wave function. It's a wave function. So wave function is uh, what do you mean by wave function? So if you want to describe in quantum mechanical terms, if you want to describe a system, then that is given by the wave function. Okay, and this is called the ket and rod. So it's a quantum state. Then the action of the operator on the state is denoted by the operator A acting on this wave function. Okay. So we have different operators for different observables or different measurable quantities. Like for energy, if you want to measure energy, then the operator corresponding to it is called the Hamiltonian operator. So Hamiltonian operator corresponds to the total energy of the system. Similarly, magnetization operator magnetization operator Ix, Iy, Iz represent the component of magnetization along the different axes. So Ix, Iy, Iz, these also you can operator. So these are the operators for representing the components of magnetization along different axis. So this wave function is actually an eigenfunction. So whenever an operator acts on an eigenfunction, we get an eigenvalue and the corresponding eigenfunction. Okay, the eigenfunction will remain unchanged, and we will get an eigenvalue when this operator will act on this eigenfunction. So if psi is the eigenstate of an operator, then this operator acting on this eigenstate will give us a value of a, and the eigenfunction will remain same as that. So here, what is a? This small a is the eigenvalue. It is the eigenvalue corresponding to the operator a. Okay, so this is the basic concept of operator in quantum mechanics. So here a is the operator. This operator is acting on the eigenfunction psi, and we get an eigenvalue a, and the eigen function remains the same. So operator is anything you can consider in mathematics, like we do ddx, derivative of e to the power x, right? So here d by dx is an operator. Okay, and this is the eigenfunction. So what we get when we do this, the the eigenfunction remains as eigenfunction. But if we do a derivative of a e to the power x, then what do we get? We get a e to the power x. So here what d by dx is? D by dx is an operator, and this is acting on the eigenfunction a e to the power x. And when this operator acts on this eigenfunction, we are getting an eigenvalue. This is a. A here is the eigenvalue, right? And e to the power x remains as e to the power x. So this is the eigenfunction. So that is what is operator what an operator is in quantum mechanics. Okay. So now let's move into what is density operator or density matrix. So density operator rho describes the state of an ensemble of nuclear spins. It is used to deal with a system that is in a statistical mixture of different states. Okay. So we have in a sample we have an ensemble of nuclear spins. We have a number of nuclear spins, and these nuclear spins are randomly oriented. So if we want to deal with such a system in which which has multiple nuclear spins, then that can be described by an operator, density operator, called density operator. So the state of a spin system using a wave function psi of t, which can be expressed as psi of t summation over m cm whole t umi. So what is umi over here? Umi are orthonormal basis function, and cm of t are time dependent coefficients that describe the state of a system. So if you want to describe a system, if you want to describe a spin system of such a nuclear spin system, then that is described by this wave function, which is this summation over m. M is the what is m over here? M is the number of or the collective number of nuclear spins over here. Okay, and this is the we get so summation over this orthonormal basis function and the c and the time dependent coefficient. Okay. So the matrix found by the ensemble averages of the products Cm of t and Cn of t is represented by another operator rho, which is defined as n rho of t m Cm t o star Cn whole t. Okay. So just give me a second. So I will add one more slide so that we can understand this concept in a bit more detail. So basically, what is happening over here is that the the state of spin. So the state of a nuclear spin, state of a nuclear spin or state of a spin can be described by a wave function, right? It can be described by a wave function, can be described a by a wave function, and this wave function is of the form psi of t equal to summation all over m c m t u m I. Okay. So what is Cm of t over here and UMI over here? So CMT is the so what we saw in this one over here is the Cm is the it is a time dependent coefficient, right? It is a time dependent coefficient, and UMI is the orthonormal set of orthonormal set of basis function. Okay. Now we also know that in quantum mechanics, when we make a measurement, when we make a measurement of an observable of the spin system, we observe the time averages, or equivalently the ensemble average of its value and the average value of the observable. Okay, the average value of the observable of the spin system is described by the expectation value of the corresponding operator. So we will look into what is the expectation value of the operator in the upcoming slides. But first, what let's understand this concept first. So the density, you understood what is density operator. So the density operator is a matrix whose elements represent the populations and coherences of the quantum states in the system. So density operator is basically a matrix, and so in a matrix you will have elements. So the diagonal, we will look into what is in the upcoming slides. We will look into what are diagonal elements and what will the off diagonal elements represent. So the diagonal elements and the off diagonal elements represent the populations and coherences of the quantum state in the system. Now, for a single spin half particle, the density matrix is a 2 into 2, 2 into 2 matrix. Okay. For a spin now, if there are n spins, n half spin, then the density matrix will be what? It will be 2 to the power n into 2 to the power n. Why 2 over here? Just Yeah. So why is it two? Why is it a for a single spin? So if there is only a single spin half particle. So if there is only a single spin half particle, then the density matrix will be 2 into 2. Why is it so? Because we know that each nuclei can exist in two states. One is the alpha state and another is the beta state. Okay. So since density operator it is a matrix, and we have two state for each nuclei, so it will be a 2 into 2 matrix. Now similarly, if there are n number of spins, n number of nuclear spins, so for n number of nuclear spins, what we will get? What will be the density operator? The density operator will be 2 to the power n into 2 to the power n. Okay, so for example, if there are two nuclear spins, okay, if there are two spin half nuclei, if there are two spin half nuclei, then each nuclei can exist in alpha state and the beta state. Each nuclei can exist in the alpha state and the beta state. So for one nuclei, we will have two, and so one nuclei can have alpha and beta state, and similarly, the second nuclei can also exist in the alpha state and the beta state. So that is why what we will do, we will do 2 square into 2 square. So 4 into 4 matrix. So a 4 into 4 matrix has how many elements? So a 4 into 4 matrix has 64 elements, right? 16 elements. So that is why for a system of n spins half, the density matrix is a 2 to the power n into 2 to the power n matrix. And here, so this is so how does a single spin half system look like? Now this density operator is denoted by the symbol rho. So this density matrix operator will look like this: row up, down, row spin up, row spin down, down. Okay, so like we had looked into, we had also seen this concept that it can exist in alpha alpha. So up means alpha alpha, up spin up alpha beta, beta alpha, and beta beta. So that is what is represented in a density operator. Okay. Now try to solve this question. So for a three spin system, the density operator will have how many elements? Option A 9 elements, B 6 elements, option C 64 elements, and option D 3 elements. Okay. Try to solve this question. So you have to apply the concept that I discussed in the previous slide. So here the case is of a three spin half nuclei system. So for a 3 spin half nuclear system, you have to calculate how many elements will be present in the density operator. Okay, so since there are 3 spin half nuclei, so the correct answer is option number C. So for a 3 spin spin half system, so there are 3 spin half nuclei. Now each nuclei can exist in alpha state and beta state. So so it will be 2 to the power 3, right? So it will be 2 to the power 3. So spin number 1 can also exist in alpha and beta state. Spin number 2 will have 2 states, alpha and beta state. Spin number 3 will also have 2 state, alpha and beta state. So so total number of states that can be possible is 2 to the power 3, and the number of elements that will be present for this 3 spin system will be 2 to the power 3 into 2 to the power 3. That is 8 into 8 equal to, so 8 will be 8 cross 8 matrix, and 8 cross 8 matrix will have how many elements? It will have 64 elements. Okay. So we will look into the solution. Just a second. Yeah. So each spin half particle has 2 possible states, right? It will have 2 possible states, spin up and spin down for a single. Yeah. So for a single spin half system, for a single spin half system, the density operator is a 2 cross 2 matrix which will have 4 elements. So if it is a single spin half system, the density operator will have 2 cross 2 matrix and it will have 4 elements. Now, if there are n possible states, then it has if for a system which has n possible states, then the density operator will be n cross n matrix, and the number of elements in this matrix will therefore be n square. And what is n over here? N is 2 to the power n. So for the 3 spin system, the density operator will have 2 to the power 3 into 2 to the power 3 equal to 64 elements. Okay. So it will have 64 different elements. Now, yeah, so as I was saying, the what are the diagonal elements represent and the off diagonal elements. So in the matrix, yeah. So in the matrix, what you will see that as you were seeing that row, so these are the diagonal elements. Okay, and these two, so these ones, this you can also call as row II. Okay, row II or row JJ. So these are the diagonal elements, row II or row JJ. These are the diagonal elements. These are the diagonal elements, and these ones are the off diagonal elements or row IJ. You can also call this row IJ or row JI. So these are the off diagonal elements. So what do these represent? These are the off diagonal elements. So what do the diagonal elements of the density matrix represent? The diagonal elements of the density matrix represent the populations of the quantum state in the system. So what is the population of the quantum state in the system? That will be given by this diagonal elements. And so the diagonal elements rho II, like I was saying, rho II of the density matrix correspond to the probability that the system is in the I state, in the state I. So what is the so this rho I will what does it give us? It gives us the what is the probability that the system exists in the state I. Now these elements, this rho II, these are the real these elements are real numbers and describe the populations of the quantum state. So what is the population of the nuclei that is existing in this state, in this alpha state. Okay, or rho I or II state, if you consider this as I. Now, for example, if you have a spin system with states alpha and beta, the diagonal elements tell you the likelihood that a spin is in the alpha state or in the beta state. So if you have two states, alpha and beta, then these diagonal elements, what will it give you? It will give you the what is the likelihood or what is the probability that the spin is in the alpha state or in the beta state. Now these off diagonal elements, what are these off diagonal elements? As I was saying that rho ij, where I is not equal to j, it represents quantum coherences between the state I and j. Now these elements, the off diagonal elements are complex numbers and these describe the phase relationships between different quantum states. So what is the phase relationship between the different quantum states? And they are also crucial for understanding the behavior of the system in terms of interference effect, phase coherence, and superposition of the quantum states. So what do we mean by the phase coherence? So phase coherence refers to the situation where different quantum states are correlated in such a way that they have a definite phase relationship with each other. This is essential for phenomena like constructive and destructive interference, and it plays a central role in how we detect NMR signals. The off diagonal elements of the density matrix describe this coherence between spins in different energy levels. So what is the coherence between spins that are in different energy levels that is given by this off diagonal elements? Okay. So I hope these points are clear to you. So these density matrix, density operator is basically a n cross n matrix. So what is n over here? N is the number of states that is that are possible for a nuclei, number of states that are possible for a spin nuclei. So that is the so that so that is called the that is called the density operator. So density operator is a basically an n cross n matrix, and this n cross n matrix will have elements. So what do these off diagonal elements and diagonal elements in this matrix represent that we have just now seen? Now, just a second. Okay. So what we saw just now is this: if it is an n cross at n matrix, and if there are, so these are the rho I, right? Okay, so this rho I and rho JJ, they are the diagonal elements. So these are the diagonal elements, and this rho IJ and rho JI, these are the off diagonal elements. So in a density operator, these rho II and rho JJ, these are the diagonal elements, and this rho IJ and rho JI, these are the off-diagonal elements. And so what we saw that these diagonal elements, these are real numbers. Okay, these are real numbers, and these are real numbers. And what does what do these this give us? So these diagonal elements give us, or we can say that it represents these diagonal elements. It represents the probability of a particular nuclei to exist in the I state or in the J state. Okay, so that is given by diagonal elements. And what do these off diagonal elements give us? What do these represent? So these off diagonal elements, these represents the phase coherence. Okay, so what is the phase coherence of a particular nuclei with another nuclei in a different energy state? So that will be that is given by this off diagonal elements. Now moving forward, so this question was asked in week 6. So this questions, what does it ask you, tells you to find out? So the off diagonal elements of the density matrix represent the time evolution of isolated spins in the energy levels, the deviations from equilibrium populations, the phase coherence of the spins in different energy levels, and the population of the spins in the individual energy levels. So based on the concept we discussed now, just now, try to solve this question. So out of these four options, which will be the correct one? I give you one more minute to answer, to try out this question. So yes, uh, so just now we had seen that the correct answer for this question is option number C. That is the phase coherence of the spins in different energy levels. So what does the off-diagonal elements of the density matrix represent? They represent the phase coherence of the spins in different energy levels. So this was a direct question. So because these off-diagonal elements of the density matrix represent the coherence between different states in the quantum system, capturing their phase relationships and correlate. So what does this capture? It captures the phase relationship and correlations. Okay. Okay. Now we will look into what is the expectation value of an operator. Okay. So what do you mean by this expectation value? So the expectation value uh, of an operator in quantum mechanics represent the average value of a physical quantity that is expected to be measured in an experiment given the system's quantum state. So given the system quantum state, what is the expected expected, what is the value that we are expecting for the quantity that we are measuring is called the expectation value. So if there is an operator A corresponding to a physical observable, like it can be magnetizations, angular momentum, spin angular momentum, or energy. If and there is an operator which is corresponding to any physical observable, and rho is the density operator representing the state of the system, then the expectation value of A is given by the trace of the product of the density operator and the density operator and this operator A. Okay. So how do we read this? So the expectation value of A, or expectation value of any observable quantity is given by the trace of the product of this density operator rho and the measurable and the observable quantity that we are measuring. Okay. So the trace is used to compute. So the trace is used to compute expectation values of observables which are linked to measurable quantities. And what is trace? So trace of you have in the mathematics, you know how to calculate the trace of a matrix. So trace is what? It is the sum of the diagonal elements of a square in a square matrix. So that is what is called the trace of the matrix. Okay. So the expectation value of the magnetization components mx, my, mz can be calculated using the trace of the product of density operator and the corresponding magnetization operator. So if, for example, if we are measuring if our observable quantity that we are measuring is magnetization, then what will be the expectation value of this magnetization? So it will be the trace of the product of this density operator rho and the magnetization operator. So M, okay. So suppose Mx is the operator corresponding to the magnetization in the x direction. The expectation value of Mx in this state described by rho is, so expectation value. So we are indicate this expectation values within this using the symbol. So Mx is so this is the expectation value of this magnetization in the x direction will be given as trace of the product of the density operator rho and the magnetization in the x direction. Okay, so the expectation value corresponds to the average value of the x component of the magnetization. So what is the average value of the expected x component of the magnetization is given by this expectation value. Now, try to solve this question. Once we have understood this one, try out this question. So just now we had seen that if rho is the density operator, then the expectation value of the mx operator or magnetization corresponding to the x direction will be given by what? It is given by the of trace of the product of this density operator and the magnetization in the x direction. So yeah, the correct option is option number C. This is a direct question. This does not require any further explanation. The direct question. Now, so I hope you understood this concept, expectation value. So first let's look into what all did we cover in these few slides. So first we understood that any observable quantity, if you are trying to measure it in quantum mechanics, then that is given by a wave function. It is defined by a wave function, and this wave function is what? Is summation of m, Cm of t, u, m, I. Okay. Now, what we are doing now, we also now we know that in quantum mechanics, when we are making a measurement of an observable of the spin system, we observe the time average or equivalently the ensemble average of its value and the average value. Okay, so the average value of the observable of the spin system is described by the expectation value of the corresponding operator. So the expectation value of the operator A. So if we want to calculate the expectation value of this operator A, then that will be given by what? So that is given by psi A. So these all things were discussed in the lecture. So it is, so what we can write next is psi star A psi D tau. Okay. So now, for example, the expectation value of mx, the operator for the x component of the magnetization in terms of the function umt will be given by what? So if you want to calculate the expectation value of the mx, expectation value of mx, so now here the operator is mx, so that will be given by what? Psi m, psi n, Cm of t star Cn t. So what we are doing is we are expressing it in terms of the function UMI. Okay. Now, in brief, what we can write this? We can write this in this form. Psi mx psi t star. So in place of this UMI, we can write what this m mx n. Okay. So what are these? So these are constants. So these m, this one, what are these? These are constants. These are constants, and any variation of mx results essentially from the changes in the coefficients. So these are the coefficients. So these are the coefficients, and these are the constants. So we are looked into, these are the coefficient, and these are the constants. So any change that will result, or any variation in mx that we see will be due to this, will be due to this changes in the coefficient. Now, these products of these coefficients, Cm of P star, Cnt, can be conveniently arranged in the form of a matrix, and it is useful to treat this matrix as made up of matrix elements of a time-dependent operator, P of t, operating on the basis set of function. Okay, so this one. So these coefficients uh, will result in will result in the variation of this magnetization in x direction, and so these can be represented as a basis set of function. So n, you can write it as c n of t into c m star. Okay. Now in this notation, this psi mx psi. So what we can do, so we will replace this one, the Cm of t, Cn of t in this form. Okay, Np of t. So what we have done is we have treated this matrix as made up of matrix elements of a time dependent operator P of t, right? P of t. So what we will do is now what we know is that this summation over m, this this becomes equal to 1. So since this becomes equal to 1, now we can this equation reduces further, and we can write that psi mx psi is equal to, okay. Now this is what is called the trace. Okay, this is called the trace P m of x, or P not P or rho m of mx. Okay. So in so this is what is the expectation value. So rather than writing this, what we are writing is like we are writing this one directly. Okay. So this is the expectation value of magnetization corresponding to the x direction. And it is given by the trace of the product of the matrix representations of trace of the product. So this is a matrix, and this mx, this is another matrix. So product of these two matrix, you have to do the multiply these two matrix, and the matrix that you get, the trace or the sum of the diagonals of that sum of the diagonal elements of that matrix will give you the expectation value of the of this operator mx. Okay. Now one more thing to note over here is what. So one more thing to note is that this P, you can prove that P is a Hermitian operator. Okay, is a Hermitian operator. Okay, so P is a Hermitian operator. So then writing this, you can also write it in this form. Okay. Now, if we are dealing with an ensemble of spins, so if so, this was the case of single spin. Now, if there are so if there are two, so here there were only one spin if we consider, so it can be written as this. But if we are considering an ensemble of spins, now in that case what will happen is that different spins will have different wave functions, in the sense that the coefficient, so these coefficients that we saw, that the c n star s, so this coefficient c n star s will be different for the individual spins. So if there are an ensemble of spins, then this Cn star S, this coefficient will be different for individual spins. And in such a case, what we have to do, we have to take an ensemble average of these products to derive an average expectation value of the operator. So what is the average expectation value of the operator that we have to do? And so how do we get that? So, so average. So average of the expectation value of an ensemble of spins will be given as summation of m over m summation over n c m t star c n t average m t mx n, right? So this matrix is formed by the ensemble average of the products of CMT of T, Cn of T, and this is represented by another operator rho. So this is this ensemble average of all the nuclear spins which are having different coefficient values. So that can be expressed in this form, and this can be defined. This can be defined by another operator. So here now what we get is the density operator. Okay, so this is how we get the density operator. So this operator rho is called the density operator. Okay, this rho is called the what? It is called the density operator. This concept is clear now. Okay. So now we are done with the entire concept of this density operator. Now what we will do is we will understand the equilibrium density operator. What is an equilibrium density operator? So the equilibrium density operator rho EQ describes the quantum state of a spin system when it is in thermal equilibrium with its environment, typically in the presence of a strong magnetic field V naught. So what is equilibrium density operator? It is denoted by rho EQ, and it describes the quantum state of a spin system. So what is the quantum state of a spin system when it is in thermal equilibrium with its environment and in the presence of strong magnetic field? That is called the equilibrium density operator, rho EQ. Okay. Now at thermal equilibrium, what happens is that the population of nuclear spins are distributed according to the Boltzmann distribution. With the so what we had seen in the very first lecture itself, that what is Boltzmann distribution. So in presence of the magnetic field, the energy of the nuclei gets degenerated, and it can exist in two different energy levels. One is the alpha state and another is the beta state. The degeneracy gets lost. So here all the nuclear spins exist in the same energy levels, but when this magnetic field is applied, the degeneracy is lost, and it leads to splitting of the energy levels. And this splitting of the energy levels results in two different energy state. One is the alpha state and another is the beta state. So the Boltzmann distribution gives us that what is the population of the nuclei in the lower energy state of the alpha state, and what is the population. So it gives us a ratio. It is basically a ratio of n alpha by n beta. So what is the population difference between these two energy state? Because this population difference is what leads to the NMR signal, right? So and we know that this being in the lower energy state, the number of nuclei occupying this energy state are more comparative or relatively they are more than those occupying the beta state. Okay. So yeah, so that is what we were seeing here. At thermal equilibrium, the population of the nuclear spin states are distributed according to the Boltzmann distribution, with the lower energy states being more populated than the higher energy state. Now, the interaction of the nuclear spins with the external magnetic field, we not. Now, so what happens is when the nuclei is spinning, it also has a magnetic dipole moment of its own, and this magnetic dipole moment also produces a results in formation of a magnetic field. So each nuclear spin has an associated magnetic field will produce a magnetic field surrounding itself, or it will produce its own magnetic field due to its nuclear magnetic moment. And the interaction of the external magnetic field with this magnetic field that is produced by this nuclei is described by this Hamiltonian. We have seen that this Hamiltonian operator is for describing the the energy. What is the energy of a what is the energy associated with a particular energy state that is given by this Hamiltonian operator, and it is equal to minus gamma V naught Iz. Now the equilibrium density operator is directly, so the equilibrium density operator rho, it is directly related to this Iz operator system. So it is equal to this Iz operator, and that is rho equal to 1 by z plus k by z I z. Okay. So here what is k? So where k equal to gamma h naught or gamma h v naught by k t. So what is K over here? K is the Boltzmann constant, T is the temperature, and V naught is the externally applied magnetic field. Okay. So before moving to this to the next question, let's understand this concept once again in more detail. Hmm. So what we were discussing is the equilibrium density operator. Okay. So EQ. So, so how do we get this equilibrium density operator? So first, what the matrix element rho mn. Okay, rho mn, rho ij. So anything you can write. So this matrix element rho mn is given by the coefficient Cn, the product of this coefficient and average of this. So the coefficient Cn. Now what happens is coefficient Cn. These are complex quantities. So these are these stars that have this star. These are the complex quantities, and they are an ensemble average. They represent an ensemble average. So you can write it in this form: m of t, c m of t star e m alpha n minus alpha m. Now, what does this alpha s represent? So this cm, these represent the amplitude. These represents the amplitude. These represent the amplitude, and this alpha s, which means the alpha m and alpha n. What does this represent? These represents the phases. These represent the phases. Okay. Now, what we can write this rho mn, we can write it in this form. The del mn e to the power minus en by kt. En by kt by z. Okay. Now, this z is called the partition coefficient, or this is called this partition function. We will look into what is a partition function. So this partition function is given by this equation. It is summation over n starting from n equal to 1 e to the power minus en by kt. Okay, en by kt. So what it is basically, so if you break it down, you will what you can get is the summation n equal to 1. This one will be 1 minus en by kt plus 1 by 2 factorial en by kt whole square. Then again it will be minus 1 by t factorial En by kt cube and so on. Okay. So n, what does this n represent over here? So this n is the number of states. N is the number of states. So n over here is the number of state and under high temperature approximation. So if the temperature is high, then what you can do, you can neglect these quantities, these higher order quantities. And then what you will have is, so at high temperature, you can ignore the higher order quantities. And so what we were getting is this one, this summation. What was that? It was n equal to 1 to n, this one, then 1 minus En by kt plus 1 by 2 factorial En by kt whole square. Okay, whole square. And this will continue. Now, in case of higher temperature, you can neglect these higher order quantities and be taken as 0. And then what will be left will be, okay, so this will be left. Okay, now if you solve this one, this will be 1 minus summation starting from n equal to 1 to capital N En by, so you can take this outside 1 by kt, right? This out. En. Now for Z-band interaction, what happens? This was Z-band interaction, this one, this value, this summation. So next what you can write is the summation n equal to 1. So this is 1 basically. This is the constant 1 minus. Now this becomes 0. Okay, this becomes 0. And this you can write summation. So what you are left with this is this. And so why this value basically this value. So Zeeman interaction, what happens? This summation n over 1, n equal to 1 to capital N to the number of states En. En, this value becomes 0 for Zeeman interaction. So now what we are left with is this Z becomes equal to summation n equal to 1 n. So it becomes, this becomes n. Directly we get n. Okay. So this partition function is basically the number of, it becomes equal to the number of states, right? So we found that the number of states possible. So that becomes equal to the partition function. Okay. In case of Zeeman interaction. Now, now, now try to answer this question first. Then we will move into more concepts, understanding more concepts. So yeah, so this equilibrium density operator is related to Iz operator, Ix operator, Iy operator, or it has no relation to angular momentum operators. So just now we saw that this rho equilibrium, it is equal to what? It is directly proportional to Iz. Okay, so this the correct answer for this question is option A. And we also derive the expression for rho equilibrium, right? So it becomes equal to this 1 by Z plus K by Z into Iz. So that is why the equilibrium density operator is related to the Iz operator. Okay. I hope these concepts are clear till now. So yeah, so the correct answer is option A. So the IZ operator represents the component of angular momentum along the z-axis. Yeah. So we know this, and at equilibrium, the spins are predominantly aligned along the z-axis due to the external magnetic field B naught. Right. So what happens in equilibrium? In equilibrium, this bulk magnetization also we have seen the concept of bulk magnetization. So the net magnetization in the z direction of all the nuclear spin, it becomes it gets aligned along the z axis. It gets aligned along the z axis because the number of spins in the alpha states are more. So we get a net magnetization in the z direction in equilibrium, and so this equilibrium density operator is related to the IZ operator. Okay. And also we had seen that, so what is this equilibrium density operator? So equilibrium density operator, it describes a quantum state of a spin when it is in thermal equilibrium with the environment. So when it is in equilibrium with the environment, this will align in the z direction. And so it is related to the IZ operator, or what is IZ operator? It is the angular momentum along the spin angular momentum along the z-axis. Okay. Now, what do you mean by this hypothesis of random phases? So the hypothesis, just a second. Okay, so the hypothesis of random phases, it assumes that the phases of the individual quantum states in an ensemble are random. The we saw that the nuclear spins, they are it is a they are oriented randomly, and so this an ensemble of this nuclear spins are is what gives the concept of hypothesis of random phases. And this means that there is no coherent phase relationship between the different quantum states, which has significant implications for the density operator. Now, what happens is that at thermal equilibrium, by this hypothesis, all values of the alpha, all values of the alpha state in the range 0 to 360 degree are equally probable. They are equally probable. So that is what is the hypothesis of random phases, and hence the ensemble averages vanishes for m not equal to n, and that is so basically what happens. So we were looking at rho m n, right? So this when this m is not equal to in thermal equilibrium, what happens? The off diagonal elements become zero. Basically, off diagonal becomes zero, and so that is called that. So that is what they are saying here, that the ensemble average vanishes for m not equal to n. So you can look in row II, or you can write it as row MM, row MN, row NM, row NN. So for these cases, m is not equal to n. So in these cases, in thermal equilibrium, what happens? This off diagonal elements means this one, row mn and row nn. These ones, no, these are the diagonal elements. These ones, row mn and row nm, these becomes zero. Okay, but so the non-vanishing of off diagonal elements. So if these off diagonal elements are not zero, then what will that imply? So that will imply the existence of phase coherence between the states. So the diagonal elements CEM square represents the probability that is given by this Boltzmann distribution rho mn. Just now I derived this rho mn delta mn e to the power minus en by kt by z. Okay. So is this point clear? So what is this hypothesis of random phases telling us? So the hypothesis of random phases is telling us that in thermal equilibrium, the off diagonal elements becomes zero. So if it is not zero, if the off-diagonal elements are not zero, then that would imply that there is a phase coherence between the states. So that is not done. So in this case, the thermal equilibrium, these off-diagonal elements become zero. So now try to solve this question. So hypothesis of random phases lead to the following in the equilibrium density operator. So in the equilibrium density operator, we saw that this hypothesis has an important implication. So in the equilibrium density operator, what will happen? In case of this when this hypothesis of random phases operate, so first option is diagonal elements in the random phase, diagonal elements in the density operator become zero. Off diagonal elements in the density operator become zero. Both diagonal and off diagonal elements become zero, and fourth option, it has no effect on the diagonal and off diagonal elements of the density operator. So just now we saw what will happen. To think about this question, to read this question again and then uh, then try to answer this. Yeah, so the correct answer for the question is that the off-diagonal elements in the density operator will become zero in equilibrium density operator in case of the hypothesis of random phases. Okay, now there is one more question. So for a two-spin system I equal to half, which of the following is true? So this IZ operator on the acting on this alpha alpha spin system, what will it result in? IX operator on alpha alpha spin system, what does it yield? IY and IZ operator acting on this alpha alpha spin system, what does this result? Yeah, so try out this question. So how will you solve such type of questions? Try this question and then we will look into this. Okay, so what we will do, we will try to solve this question now. Now, what happens that in a two spin system? So what happens in a two spin system? So in the two spin system, each spin will have I equal to half, right? In a two spin system, each of the spin will have what? It will have a I equal to half value. Okay. Now in the two spin system having spin I equal to half, their spins can be represented in so we can represent the spins of this system in spin up and spin down state, right? So spin up and spin down. So spin up means what? So spin up is called the alpha state and the spin down is called the beta state. Now this alpha state, this spin up state represents this spin up state. It will represent what? The spin up state, it will represent or it will have a spin magnetic quantum number of plus half, and the spin down state or the beta state represent a spin down state having ms equal to minus half. Okay, so the two spin states. So the two spin states will be what? What will be the two spin system? So the two spin states will be alpha alpha, alpha beta, beta alpha, and beta beta. Beta beta. Okay. So now the spin operators. So if the spin operators act on the spin state. So in this question, what is asked that if the spin operator, there are different spin operators, Iz, or the angular momentum along the z-axis, Iz, if it acts on the spin system alpha alpha, what will we get? What will happen if Ix operator acts on this alpha alpha spin system? What will happen if Iy operator acts on this alpha alpha spin system? Okay, so yeah, so that is what is asked in this question. So if anyone has solved this, the correct answer for this question is option number A. So now let's look at how you have to solve this question. So so just now what I had discussed is that in a two spin system, where each spin has I equal to half. So in a two spin system, each spin has I equal to half, and each spin can exist in two state, alpha state or the beta state. And so there can be four possible states: alpha alpha, alpha beta, beta alpha, and beta beta. Now if the spin operators Ix, Iy, and Iz acts on the state, they can act in the following ways. So what is Iz? Iz basically it measures the projection of the spin along the z-axis. And this Iz operator, when it acts on the spin of a system, what does it return? It returns the eigenvalue of ms. This is the magnetic quantum number when acting on a state. Okay, so if this Iz operator acts on the alpha state of a nuclei, what we will get? So for alpha state, we know that the magnetic quantum number is plus half. So we get plus half alpha. Now similarly, if this Iz operators acts on the beta state, what we will get? We will get minus half alpha. Okay, so minus half beta. So not alpha, it will be beta. Okay, it returns it will return the eigenvalue of the magnetic quantum number when it acts on a state. So when this Iz, so what will happen is this when this Iz, now what will happen if Ix acts on the alpha system? Okay. So we just now learned that if this Iz operator acts on the alpha state, then it returns the magnetic quantum number of that state, magnetic quantum number of that state. Okay, now what will happen if the Ix operator, if Ix operator acts on the, so what this Ix will measure? It measures the projection So Ix operator, it measures the projection of the spin along x-axis. It measures the projection of the spin along x-axis. And what does it return? The Ix operator returns it mixes the alpha and beta state. Okay, it mixes the Ix operator, it mixes the alpha and beta state. It mixes the alpha and beta state. So what do we get? So we get if Ix acts on on the alpha state, what we get is plus half beta. So it mixes the alpha and the beta state. And if this Ix acts on beta, then what we will get? We will get plus half alpha. Okay. Now what will happen if Iy acts on this? So what will Iy measure? It will measure the projection of the spin along the y-axis. Along y-axis. Okay. And what will happen when this Iy acts on the spin state? So when this Iy acts on the alpha state, what we get? It introduces a phase factor. Okay. It introduces a phase factor. Okay, it will introduce a phase factor. So when this Iy operator acts on the alpha state, we get I by 2 beta. And when this Iy acts on the beta state, what we get? We get minus I by 2 alpha. Okay, now we will after we have come to know all these points, we will apply this concept on the question that is asked. So remember that what happens when this IZ operator acts on a spin nuclei on a spin state, what will it do? It causes it returns the magnetic quantum number of that state. So for alpha state, we know that the magnetic quantum number is plus half. So we get half alpha. Okay. Similarly, when this IZ operator acts on beta spin state, then it returns for beta, the magnetic quantum number is minus half. So what we get is minus half beta. Now, similarly for Ix, what does it give? It mixes the alpha and beta state. So what happens whenever this Ix operator acts on this alpha state, we get plus half beta. And when this Ix operator acts on beta state, we get plus half alpha. And for Iy, it introduces a phase factor, that is I by 2 beta and minus I by 2 alpha. Now, after knowing this, when we apply this one, add another. So now in the question, these operators, so these operators are acting on this. So this Iz, Ix, Iy, Iz, these operators are acting on the alpha alpha spin system. So what will happen? So what happens is this Iz operator. So each of these operator acts individually on the nuclear spin state. So first this Iz will act on this alpha. So when this acts on alpha, what we will get? We will get plus half alpha and then this will act on this another this state alpha. For that also we will get plus half alpha. So when this Iz operator acts on this alpha alpha state, what we get is plus half alpha alpha. So when this Iz operator it acts on this alpha alpha spin state, we get alpha alpha. So that is why the option in this question option 1 was correct. Okay, now in this case, what now if this Ix operator, now we will look into why the other options are correct. So if this Ix operator acts on this alpha alpha, what will happen? So again, so what we will get? So first this IX operator will act on alpha, and what we saw that this IX operator, what it does is it mixes the two state. It mixes the two state. So for alpha, we will get what? Plus half beta. Okay. And when this one will act on IX, just a second. So yeah. So what we are getting here. Now similarly, we can also calculate what we will get if IY acts on this alpha alpha system. Then this IY will act on alpha and it will give us I by 2 beta. Okay. And so what we get here is that when this IY alpha alpha, we will get I by 2 beta alpha minus I by 2 alpha beta. So the option number C is also incorrect. So this is so this one is incorrect as when it we do not get this alpha alpha. Okay, we do not get alpha alpha, right? We do not get alpha alpha. And when this IX alpha acts on this IX, what do we get? So when this one acts on this alpha alpha state, we get half beta alpha plus half alpha beta. Okay. So option number B is also incorrect. So the only option that is correct is option number A. Is this concept clear? So IX it mixes the two spin system. So when this IX acts on first, it will act on alpha. We will get half beta, and then again this will act on this half beta, and we will get half alpha. So that is why we see that here alpha alpha is getting mixed into beta alpha and plus half alpha beta, and this IY it introduces a phase factor. So we get half beta alpha minus half alpha beta. Okay, now yeah, we were discussing the concept of partition function. Just a moment, give me a minute. So yeah, we had derived the equation for partition function. So partition function Z, it provides a way to sum over all the possible states of the system, right? And it is given as Z equal to summation over n e to the power minus En by kT. En by kT, where what En is? En is the energy of the nth quantum state. En is the energy of the nth quantum state. And T is the Boltzmann constant and T is the temperature, absolute temperature. So for a spin with I equal to 5, so try to solve this question. Yeah, we had derived this also in this slide, if you remember. Z. Yeah. So from this equilibrium density operator, we had derived the partition function. So this partition function is basically, I discussed that it is the number of states that are possible. Number of states that are possible, basically. So now try to solve this question. So for a spin with I equal to 5 by 2, what will be the partition function? So the options are 5 by 2, 3 by 2, 6, and 4. So basically, this question is similar to what we had seen in the initial lectures, that if we are to calculate that how many orientation or how many states are possible for a particular spin quantum number. So what formula did we used to apply? We used to apply this formula 2i plus 1. So in this question also we have to apply the same formula, because we saw that summation over this n equal to 1 to n z, what we were getting? We were getting n, right? So that is why this will you have to directly find the number of states possible. So 2i plus y, so that will be 2 into, so for spin I equal to half, it was 2i into half plus 1, it was 2. Now in this case, the I is 5 by 2. So you put 5 by 2 and you get calculate the value. So it will be how much? It will be 6. Right, it will be 6. So the correct answer is option number C. Yes. No, the correct answer is option number C. The partition function for a spin with I equal to 5 by 2 is simply the number of possible quantum state. Okay. Why is it equal to the number of possible quantum state? Because here, you recall, if you recall this one, we derived. So I derived this one for that particular question, that this partition function is equal to n. What is n over here? N is the number of possible quantum states. The possible number of quantum state, and the possible number of quantum state is given by what? It is given by 2i plus 1. So that is why you directly apply the formula and you get your answer, y plus 1. So it will be, it is 6, and the sublevels corresponding to the magnetic quantum number mi can take values. So it can have values from minus I to plus I. So with increments of plus 1, with the increments of plus 1, we have seen that the quantum number, this magnetic quantum number can take values from minus I to plus I with increments of plus 1. So it will be minus 5 by 2. Then again add plus 1 to it, you will get what? Minus 3 by 2. Again add plus 1, you will get minus half. Then plus half, 3 by 2, and 5 by 2. Okay, so the partition function will have, it will be 6 in this case. Okay. Now let's discuss a few more concepts. So, so we had for partition function, what we saw that partition function given by Z. Now, for partition function, we saw that this Z is equal to, it is equal to summation n equal to 1 to n e to the power minus en by kt, where en is the number of en is the energy state, nth energy state, and k is the Boltzmann constant, and c is the temperature. Now, after this, we when we solve this further, we what we get is this one, and ultimately what we were getting is, after solving this, is this n equal to 1 to n 1, and this was equal to capital N, number of possible quantum states. Okay, number of possible quantum states. Now, if what happens is, if H is Hamiltonian, if H is the Hamiltonian and I are the eigenstates, I are the eigenstates with eigenvalue lambda I. So whenever an operator acts on an eigenstate or eigenfunction, we get an eigenvalue and the multiplied by the same eigenfunction. Okay, eigenvalue lambda I. So here Hamiltonian is the operator. So this operator acts on this function, wave function, and we get an eigenvalue lambda I and this operator. Yeah, and this function and this wave function. So if we take exponent on both sides, what will we get? We will get e to the power lambda I. So what we can write further is that this j e to the power h e to the power lambda I delta, and if we solve this, what we will get? We will get delta ij e to the power lambda I. Okay. So now why did we derive this equation? So this the number of elements in density operator. This can also be written in this for 1 by n m e to the power minus e n by kt. Sorry, give me a minute. And we will get here e 1 by n m e to the power minus e n by kt. Okay, so finally what we get here is that the density operator rho equal to 1 by n e to the power minus h by kt. Okay, so did you understand this point? So if we consider the Hamiltonian acting on this I function, then we can from the so by solving all this we can get this equation. We can get this expression. Okay, now after we got this rho equal to 1 by n e to the power minus e n by kt, we can expand this in power series. We can expand this in power series and we can write it in this manner. 1 minus h by kt, similar to what we were seeing for this partition function when we derive this partition function. In a similar way, we can also rewrite this expression, and under high temperature approximation, what we will get? We will get 1 by n, 1 minus h by k t. Okay, till this everything is okay, right? Yeah, so 1 by n e to the power minus en by kt, and we expand this in the power series and at high temperature. So at high temperatures, we can ignore the higher order factors, and this we will get this expression. Now what? Now what we know, this Hamiltonian operator is represents the energy of a the energy of an system, right? Of an spin system. So this one is what is it with gamma h b naught. It is gamma h naught I z, right? Gamma h naught I z, and this rho you can write it as half 1 plus. So basically what we are doing is we are replacing this h, and in place of h we are writing this expression of the energy of an energy level. What is the energy of a energy level? It is given by gamma h naught I z by k t. Okay, so that is how we calculate the matrix element of the operator Iz. So now if we what we will do, we will calculate the matrix element of the operator Iz. Then the matrix elements. What will be the matrix elements of rho? So the matrix elements of rho will be what? Rho alpha alpha. For rho alpha alpha, it will be half 1 plus gamma h naught by 2 kt. Right. For alpha alpha system, this Iz is what? Iz is nothing but m h cross. Right. M h cross. So for this for the alpha spin nuclei, alpha state, for the alpha state, the magnetic quantum number is half. So you replace this Iz and put replace this Iz and put half here. So you will get gamma h bar h naught by 2. For rho beta beta, what we will get? Half 1 minus, because why did we got minus here, by 2 kt, because we know that for the beta state, the magnetic quantum number is minus half. So we put for Iz, we put m equal to minus half, and that will be the value of this element, this density operator element. Similar, but for rho alpha beta and rho beta alpha, what will it be? It will be zero. It will be zero. Why is this zero? Because of the hypothesis of random phases. By the hypothesis of random phases, we know that rho alpha beta and rho beta alpha will be zero. So what we get finally? So what will be the elements of this density operator? So the elements of the density operator will be 1, 0. This is alpha alpha, alpha beta is 0, beta alpha is also 0, and beta beta is 1, plus gamma h naught by 4 kt, right? Minus 1. Okay. So now, so what we did here, we calculated the matrix element of the operator Iz for the density matrix operator. For the density matrix operator. Now for multi-spin system, multi-spin, if there are, so this is for two spin system, right? For two spin I equal to half system, we can derive this expression. But for multi-spin system, what we will get? The multi-spin system, the Hamiltonian will be what? It will come from both scalar coupling and or the J coupling and the Zeeman interaction. It will come from both the Zeeman interaction and the J coupling. So what does Hz represent over here? Hz is the Zeeman interaction. What is the Hamiltonian that we get due to Zeeman interaction? And what is the Hamiltonian that we get due to J coupling? So due to J coupling, what is the Hamiltonian? Now under high field approximation, this Hj will be very small. This Hj will be very small compared to that of Hz. And then the J coupling can be dropped for the evaluation of the elements of the density matrix. So you understand what will happen. So under high field approximation, this J coupling, this will be very will be very small. So compared to Hz, the Zeeman compared to the Hamiltonian that we were getting due to Zeeman interaction, compared to this one, this will be very small, and so we can exclude this. We can drop this, and then so for the two spin system, what will happen then? So the two spin system, we can write this density operator in this form: 1 by 2i plus 1a, 2i plus 1x, whole 1 plus gamma h naught Iz by kt. Okay. So with Iz we got what? So this Iz is what? This Iz is the Zeeman interaction. Due to Zeeman interaction, what is the Iz of this nuclei A? And this operator, it acts Iz operator acting on the spin A and the spin X. Now the eigen states of the spin of the two spin system. The eigen state of the two spin system are what? They are alpha alpha, alpha beta, beta alpha, and beta beta. Now with these states, the matrix elements. The matrix elements of the row will be, it will be equal to 1 by 4, 1 plus gamma h bar h naught by kt, rho beta beta, and for rho alpha beta, alpha beta. So these will be coupled right now. So that is why we are multiplying them. So for rho alpha alpha and rho beta 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 alpha, they will have 1 by 4. Okay. Now if we write the elements, now if we write the remaining elements, then what we will get? So the remaining elements will what? It will be 1 by 4. So the remaining elements will all be 0 other than these alpha alpha, beta alpha. Other than these, all the other elements will be 0. Okay. So 0, 1. This will be what? 0, then 0, 0, 1, 0. So basically what we are doing is we are substituting these values that we got just now for beta 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 alpha. Okay. So this is for multi-spin system. We are writing the density what will be the elements of the density operator for a multi-spin system. So one. So we have taken out this common gamma h naught by kt, 1 by 4 gamma h naught by kt, and then what will remain? This one will all be 0. For beta, it will be what? And for this beta beta, it will be -1. Okay. Now from here, what we get is this addition coefficient 1 by z plus k by z pi s I z. Okay. Now what is k over here? So here k is nothing. So I just derived this expression that we had looked into when we were discussing the partition function. So this will be gamma h. So yeah, h naught. Then this operator by get a t. Okay. So here this capital key, this k, this is not Boltzmann constant. This capital K is actually gamma h naught h bar by a t. Okay. So what all did we look into today in today's lecture? So so first of all, we looked into what are operators in quantum mechanics. One more thing I could have discussed is the time evolution. So what is the time evolution of density operator rho? But not many questions have been asked from this section in your assignment, so I didn't go into the detail of this. But what is this time evolution? This time evolution, it is an explicit understanding It gives an explicit understanding of the performance and characteristic features of an experiment. And and it is derived from the knowledge of the time evolution of the density operator through the experiment. So for this, we need to use the time-dependent Schrodinger equation. So these were discussed in the lecture, so you can go through them. But today, what all did we understand in today's lecture is that what are operators in quantum mechanics? So operators are can be considered as any um, like that we see in mathematics, we see there are different operators, addition, subtraction. So it can also be considered as similar to that. So operators act on on a wave function, and after these operators act on the wave function, we get an eigenvalue and the wave function. Okay, so these are mathematical entities that correspond to physical observables like position, momentum, energy, and spin. So any observable quantity. So for a nuclei has different observable quantity like spin, angular momentum. Then it has a magnetic nuclear magnetic moment. Then it has the spin quantum number I. So all these different quantities, mathematical entities for all these, they different operators are present. And so if we want to describe the behavior of of a nuclear spin under the influence of magnetic field and radio frequency pulses. So uh, when we were discussing about inept and other 2D experiments, NMR experiments, we were seeing that what is the experimental setup, what are the pulse sequence. So in when different pulse sequences are given, uh, what is the effect of these different pulse sequences on these observable quantities. So for understanding those, we need to understand the operators in quantum mechanics. Okay, now if there is an operator, you will always see that an operator is denoted by a symbol and a hat on top. So for the energy, the operator that is used is Hamiltonian operator, which corresponds to the total energy of system. Similarly, for the magnetization operator, Ix, Iy, Iz, they represent the different components of magnetization. And the psi is what? It is a wave function. Wave function is what? It describes it describes all the information. All the information of a particle is present in the wave function of is given by the wave function of that particle. Okay. Yeah, so I explained this through an example. So this is an operator ddx, and this is an eigenfunction e to the power x. So when this acts on an eigenfunction, we get an eigenvalue, and this is the eigenfunction remains the same. Okay, now we looked into density operator. So density operator is, we saw that it is a n into n cross n matrix. N cross n matrix, and depending on the number of spin nuclei, whether it is a single spin half nuclei, whether it is a two spin half nuclei or three spin half nuclei, accordingly we can find out how many elements can be present in the density operator. So each nuclei will have two state, alpha state and the beta state. And so that is why. So if there are three spin system, then the number of possible states will be what? It will be 2 to the power 3. Similarly, for four spin system, the number of possible states will be 2 to the power 4. So in this way, if you want to find the number of elements, then it will be 2 to the power n into 2 to the power n, where n is what? Small n is the number of nuclei in spin half state. Number of spin half nuclei. Number of spin I equal to half nuclei. Number of I equal to half nuclei is the small n, and this is a n cross n matrix, so it is 2 to the power n into 2 to the power n. So it basically this density operator, it describes the state of an ensemble of nuclear spin, and it is used to deal with a system that is in statistical mixture of different states. So in an ensemble of nuclear spin, different spins are in different states. So if you want to deal with such a system, then here the density operator comes into play, and this is a given. This state is given by this expression. This psi of t is summation over m cm of t umi. And UMI are the orthonormal basis function, and CM of t are the time dependent coefficients that describe the state of a system. Now the matrix formed by ensemble averages is represented by we can represent this by another operator, the ensemble averages that is given by this density operator. Yeah, we looked into this. So how will this operator density operator look like? So spin up, spin up, spin up, spin down, spin up, spin down, spin up, and spin down, spin down. So basically alpha, 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 beta, beta, alpha, beta, beta. Remember this one? This 2 to the power n into 2 to the power n matrix. So n is the number of spin half nuclei. So that will give you the number of elements that you will obtain in a that will obtain on a for a in the density operator. So we looked at this question. Then we looked at what will be the off diagonal elements and the diagonal elements. So the diagonal elements represents the probability of a particular nuclei to stay in that state, and the off diagonal elements, these are complex numbers, and they represent the phase coherence, the phase coherence of the spin states in different energy levels. Okay, phase coherence in different energy levels, while this diagonal elements, it represents the population of the quantum state in the system, and it is basically corresponds to the probability that the system is in that particular state. Okay, so yeah, so these are the diagonal elements, rho I, rho jj. These are the diagonal elements, and these are the off diagonal elements. And then we looked into the hypothesis of random phases. In hypothesis of random phases, this off diagonal elements becomes equal to zero. Okay. So we looked at this question. Yes, the off diagonal elements, it represents the phase coherence of spins in different energy levels. And then we also understood about the expectation value of an operator. So expectation value of an operator is what are we expecting for a particular measuring a particular quantity? What is the expected value? So that is given by what? It is given by the product of trace. So so it so the pro so what we do, this density operator, the product of the density operator matrix and this operator A. The matrix that we get, we then if we calculate the trace of the matrix, then that will give us the expectation value of that particular physical observable that we are measuring. Okay. So product of the density operator and the function that we are measuring of the observable quantity, and trace is basically the sum of the diagonal elements. Yeah. So the trace of the product of the density operator, and the corresponding magnetization operator. So if it is a magnetization operator is our observable quantity, is our observable, then it traces the it will be the trace of the product of this magnetization and this density operator. Okay. So it is, yeah, product of this density operator and mx, and then the trace of the or the sum of the diagonal elements of the matrix that we get on multiplying the density operator and the observable function. So we derive these equations. So how why is this expectation value equal to this trace of the trace of the product of these two matrices? We derive that. And then we looked into equilibrium density operator. So in equilibrium density operator, we saw that this equilibrium density operator is directly proportional to Iz. Okay. So in the equilibrium condition, the magnetization remains along the z direction. So this is why this rho becomes is related to the Iz operator. And then we looked into partition coefficient. So partition coefficient becomes equal to the number of possible quantum states, n. And then equilibrium density operator. So it is related to the Ising operator. And the hypothesis of random physics, it states that the elements in the off diagonal elements will be zero. Okay. And then we learned how to solve these type of problems. So when the different operators ix, iy, iz acts on the different spin states, alpha, 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 beta, what values do we get? Okay, we solve this question. And then function. So partition function is basically the number of possible quantum states. So that is why it becomes equal to 2i plus 1. Okay. So, so that is all for today. I hope the session proved to be useful. And if there are any more doubts, I will take up those doubts in the next class. Meanwhile, you go through the through the lectures that are being taught for week 8. And in the next session, we will solve the questions related to week 8. So thank you, everyone.